We were talking about the processes and how things in integrated circuit and devices started way back in 1900, and we came last time up to telling what technologies are available. Here is a photograph. I don't know, maybe I do this. Here is a photograph of first generation of large-scale integration circuits. This is a DRAM. Most of you are aware of DRAMs. Unless you have a large DRAM, nothing much can be done on a processor. You are expecting DRAMs of 4 GB, 16 GB, 64 GB and still say it's not good enough because your video game doesn't play fast. So that's the DRAM. The first DRAM was 4K DRAM from Intel, which is numbered 111103. The next slide shows, this is only just to show you a complexity of devices there. This is the first microprocessor from Intel, 4004. We started with one name, as I said last time, 16 ICs, 10 transistors. 70s we said 1000 transistors or something large scale, and we went to 1980s we say very large scale, and we say okay it's a 1 million times, so we say it's a very ultra large scale, maybe as I said last time giant scale or some large or very large or something will be with when you have billion transistors already we have on the chip. Okay, this is same. Just to give you the very small, initially, I don't know whether your second year lab digital, you may have certain chips which are still on bipolar. This is called 7400 series, very famous TTL series. I don't think they are manufactured now for any real system, only for I think class courses running in the different engineering institutions. Otherwise 7400 is hardly anyone uses, but that was the bipolar chip. And then of course 74000 started with CMOS chips, MOS chips, and now almost every circuit, integrated circuit chip is made out of MOS circuits. As we said, there are two kinds of MOS transistors. One has the electron transport in that, and that's called NMOS. The other is when the whole transport occurs, we say PMOS. And they together, they constitute a very powerful way of doing a circuit design, which is called complementary MOS, both P channel and N channel together. We'll see that later. One of the major person who allowed this so-called progress of integrated circuit over the years, I think there was a great person called, still exists, I'm sorry, Gordon Moore, who is the chief of Intel, who is one founder member of Intel along with Noyce and Grove, and he made in early back in 65, he made a prediction, and that's very famous law called Moore's law. What he predicted that the way technology will grow and the way circuit will be, you will be able to put transistors on a single chip will be something growth of exponential kind. Or he says every year the component density will double. And to great extent till say 2000 or 1996 time, the Moore's law was rigorously followed. Every year the components on chip were because the size of transistor we started reducing, and as we start reducing the sizes, we found that component density could increase. Now this is called Moore's first law. Later when 2000 came, he figured out that the progress in technology, though it has already reached such a high level of integration, he said okay, now it may not be every year double, maybe every 2 years it will double. And by 2006 he said every 4 years it will double. It's called Moore's third law, and maybe in 2012 he may say something else. Okay. So the Gordon Moore was the one person who has such a futuristic idea, and there is a joke we did. Most of the technology people who were making chips actually, as if they were constantly looking at Moore's law, oh I have to now reach here, as if I had to reach now here. So the progress in technology was as if to satisfy what Moore wanted. Okay. And that's how Moore's law became the most popular, and whenever we talk about integrated circuits, we always like Ganesh ki puja, vaise we always say Gordon Moore, thankful to all of you. Okay. So these are the numbers, amazingly visionary, and already as I say HPPA 850, it was by 90s. We could go up to 42 million transistors. 2 gigahertz clock on Intel P4, and the present, as I said, is 942 million transistors. We have already made a chip which has 1.2 billion transistors, but the part was there that is still not being used by designers. There are too many transistors available, but there is not a big system available which probably will require 1.2 billion transistors. 942, yes. 942 this million transistor circuit has 4 Intel cores inside with 8 cache I will see later as RAMs, and such a large circuit probably was first time made by Intel. Okay. This is the person. This is called the Moore's law. You can see, sorry. This is, you can see, this is the logarithmic scale. This is transistor per die. This is number of years. And for different kinds of devices, this is memory, this is processor, this is logic. And you can see roughly his law. And you can see now it is trying to slightly going down in the slope, which means the second law or fourth law probably will start coming, that every year it will become now, every 4 years it may become double, and later maybe I don't know. So as I said, this is a exponential growth. Important thing about this. He also predicted for the processor that how processor technology will improve. And we started with 4004. We are already dual core, and as I say, 4 core processors already reached, and then you have billion transistors roughly reaching here. Because this is 2008 data, so by 2010 already we have reached 4 core processors. So you can see why I always show these slides, because I always want to say people that how visionary one can be, and that was in 65 when at best 12 transistors were able to put on a chip. Okay. That was the time Intel made first PMOS circuit with 12 transistors on chip. And now look at it, what he thought then is proved almost correct. Okay, this is again same statement. This is some milestone. For example, as I told you, there are this is a 4 transistor circuit in 1960, first IC. Early 90s we have Pentium, okay, which, so what is most important law? What exactly he is trying to say? In a word, I say, since you are going to follow electrical engineering later, and most of you will be using chips left and right, what Moore says that the size of a transistor will actually reduce every generation by 0.7. And if you see by one side reducing by 0.7, 2 sides of a area will be 0.5. Okay. So that's why that number becoming double, 0.7 into 0.7 is essentially 0.5. So you say every year it will start doubling because in same area you can put double the transistors now. So that's what the Moore's law was saying. Now this 0.7 is really very important number for us. We started with say 5 micron technology, then we multiplied by 0.7, so it became 3.5 microns, then we multiplied 0.7, then it slowly we came to 0.6, 0.5, then we became 0.35, then we became 0.25. Just see, I just multiply the number by 0.7. So next technology node is 0.25, 0.13, which is 130 nanometers, 0.7 of that is 90 nanometers, 0.7 of that is 65 nanometers, 0.7 of that is 45 nanometers, 0.7 of that is 32 nanometers, 0.7 of that is 22 nanometers. We are now working on 22 nanometer process. The day will come when we will have 16 nanometers, then you may have 11 nanometers, then you may have 7 nanometers, and I don't know after 5 nanometer anything will come because you will cross the wavelengths. Okay. So maybe 0 wavelengths kind of circuits or something in the air, nothing visible but things are happening. This may be your time. This is Intel first 4004. This is Intel Pentium 2. This is Pentium 4 with 42 million transistors. You can see from here, there are certain uniform blocks you can see here. What could be these? Can you think? These are all logic. That is, there is a microprocessor, different parts. What could be this universally looking identical blocks? Can you think what could it be in a processor? What should we need further other than other control part and processor part? Memories. So these are the cache. okay, or cache as the word goes in the case of processors. Today silicon device is indispensable. Everything has to be controlled by silicon. Silicon has realized extremely high frequency operations. As I said, what is the kind of frequency we are working at? 2.6 gigahertz. In time will come soon when we will have frequency of 50 gigahertz. And ultimate aim we are looking for is 16 gigahertz. If I don't know, we are enough to life at 16 gigahertz in the end of maybe 2040 or 50. You can see today's IT such as internet, iMode, cellular, GPS, game machine, entertainment robots could not be realized without circuits made out of silicon. These are called application fields. If you see this, there are different kinds of electronics is used by us. One is portable electronics, handheld. Portable means handheld. PCs, there are small PCs available. PDAs, digital calculators and other systems. Wireless blocks, mobiles. The other important area which decides whether portability is one aspect, whether you want to make circuits which are smaller because you want to have a portability. Then we need cost. The major worry in integrated circuit is the cost. Typical Pentium 4 chip design required around 160 man years. Now calculate man years, okay, so many persons working so many years to get one Pentium chip design. This is called design time. And a designer in US and even in India now is almost equivalent time. Is earning around $100,000 a month. So if you have to pay so much money to create chip, okay, to design itself and then put the money on fab, the chip has to have a huge yield, 90% must succeed, and it should have a market which will take the money out of that to the company. So every sense the electronics is somewhere connected to the economics. Whether I make a microprocessor, I make other logic, I make anything, unless it is sellable to that amount, I will not invest money on that. Even if I know how to do it, who will buy it? Okay. Only companies or only people who buy anything at any cost. You know which people, even in India or abroad or in US, which people do not bother about money? Maybe government departments like ISRO or Space Department in US, NASA, or defense. In the name of defense, you can sell anything, any amount, and they will pay for it because it's a natural defense, you know. As soon as the word defense comes, including everyone says, oh, don't talk, because it's a matter of defense. So everyone becomes defensive. So the cost essentially of an IC, you will be surprised to see the cost of IC is not so much in silicon, but in its package and its cooling system. Okay? Because huge power is being dissipated. How to remove that heat? Okay. So the cost goes in more of a outside part of the chip rather than the chip itself. Chip may be cheap, but the package will be very costly. Okay. And that is where the money is essentially. So if I tell you, give a project to you tomorrow, okay, we will work on a new package. You say, sir, but usme electrical kya hai? But that's the money. But if you go to US and similar professor at Stanford or MIT gives you same project, oh, with a great thing, oh, I am doing fantastic work. You know, that's the attitudinal problem here, that I only want to solve differential equations, or I want to solve something which is more jazzy, which I can write in my CV, I worked on so much. Essential things are something which people, it's very drudgery work. You know, I'm making a new package which has a very good cooling, which has all kinds of low capacitances, low resistances. It's a very difficult task. And it's a drudgery for everyone. So most of the research in India or abroad also in universities, most cases, probably will be more on the basis of theory, more basis of thinking, physics, technology, but certainly not on making circuit packages. There are issues in integrated circuit design. One is called reliability. If I make a circuit, the word reliability means it should work on given specification for a given time. Let's say it is a reliability of 90%. So you say this is designed for 5 years. Most 90% chips will work for 5 years. Okay, that's called reliability. If the system does not remain reliable after some time, then no one will buy from me. Okay, no one will buy from me. So one worry in design is that when I design and fab the chip, It may be reliable, but over the time for which it will be in the use, it should still remain with the same specification as it started with. That's called reliability issue. There are many physical issues, essentially called migration, latches and things of kind. Then there are also issues in design called signal integrity. I have two signals going on two wires, let's say close by. We believe that two wires are separated and therefore nothing will go from one wire to the other. But in reality, there is a capacitive coupling between the two metallic wires. And if this capacitance is small enough, or large enough, then there will be a coupling between the two lines. So a signal going on one may also get into the other signal also, and which is called the noise or signal integrity issues. So these are issues which we have to solve. Then there is the issue of heat, because you will not accept it easily, but in a microprocessor, if you see any time, of course you will never see inside when it is working, but let's say I show you once something like that, you'll be surprised to see that for a given data, only some part of the circuit keeps doing lot of work, the other part of the processor area is not that much busy, okay. Now the area which is working constantly for a longer time, because the kind of data is going there, the other data may change that part to somewhere else. Those parts will actually consume power. Okay, so that part will become heated, and the other part are really not that much heated. So the energy flows from higher end to the lower end. So there is a thermal gradient. Now, some chips, some performance which are decided at 27 degrees centigrade normal operation now may fail because there is a gradient of thermal energy going elsewhere. Okay, and these issues are very crucial in actually long-term effects of any chip working in a system. The other, of course, when we design a chip, we are worried about power. As I last time made a fuss that most of you like to use mobile simply because in a newer technology, the standby power is larger than the on power. That means when you are working, it's not consuming as much, 33%. If you don't, then you consume 66%. So you probably continuously want to talk, at least to save the battery. Okay, possibly. So that's another application we are looking, and of course, as the last we say, most of the chips are separately designed for space application because space has many problems of gravity, pressures and other kinds, and therefore the designs for space are very different from the normal designs. And they cost, and if they cost, NASA, ISRO will never ask you anything, neither the government will ask them anything. Of course recently something happened, but otherwise, you say okay, it's $1 billion requirement, slowly, okay, signed. No one knows really which was required $1 billion, but it's a NASA or it's a ISRO issue. So these are the issues which we are working at. Then there are, as I say, there are different circuits have different problems. For example, if you have a portable device, our worry is battery. As I just now said, mobile, you have to keep recharging. So I want a circuit which has a large battery life. So one of the research which you can do in electrical engineering is not to work on silicon or any other semiconductor, but work on batteries. Right now there is a huge problem that, even if you have a lithium batteries, you put a mobile every second day you have to charge, or even in some cases it's draining, every 3 hours you may have to charge. So if you can make a good battery of a smaller size, which can have large ampere hours, okay, I think you will make billions, you may even earn a Nobel Prize, who knows, these days. And that's the research probably people won't like to do. People believe that it's a chemistry job. No job is anyone's. It's you who do the job and you make the money. Okay. So please think seriously, go out of the box circuits, out of the box thinking like we keep saying do this, do that. Think otherwise and say, can I make a battery which has much larger ampere hours in a smaller area? If you do that, lot of money at stake for you. Okay, everyone will rush to you. Maybe thousands and thousands of companies will pour on you for that. Okay, have a patent and everything for you. But if I say in electrical engineering battery, say yaar humko kyun? But that's an issue. The other area, of course, is telecom, military. There we are more worried about reliability because if some circuit is working in aerospace or plane or something, it should keep working. You are actually fighting with another aircraft which has an onboard computer, so you have one onboard computer. Now you are trying to actually beat the computer at the other end, and suddenly because of the heat or any other problems of reliability, your computer goes down, you are hit, there is no way you can survive. Okay. And therefore, in such systems, the major worry is reliability. Okay. Of course, there are circuits or there are chips which are called off-shelf. Okay. That is when you go to a supermarket like Hyco or anyone, from the shelf you can pick up something. Most of the circuits you don't pick up like this. But there are circuits like microprocessor, memories, which are universal, okay, and you can really go and buy any such component off shelf. So whenever you are off shelf products, you actually design it very fully, okay, and then make billions of them, and then flood the market with numbers. So the cost per circuit will become much smaller. So most off-shelf products are cheaper simply because they are made in millions and millions in numbers. But if certain processor is required for space application, how many space shuttles will go in US? Last is going now. So you will require say 100 processors. So you cannot invest huge money in hundreds, or someone should pay for that. Okay. So the question is, off-shelf products are normally not great, but they are made in millions and billions, so that the price, like for example, a microprocessor may cost the Pentium 4 highest version now, Ethereum, it may actually cost you $160. And the Pentium 4 which you use is costing now 160 rupees. Okay. So you can imagine that the kind of money can go down provided the number sale is very high. So why I always talk every class of my last 20 odd years, 30 years about money is you have to understand in engineering, it's not done for the sake of engineering. Engineering is done for marketing it, selling it, and money must get returned back to the investor. That's what the work is. So anything is good enough only and only if it is cost effective. Otherwise that, okay, you can publish a good paper, you can get much money awards on that, but no one is going to use it any time. Okay. But the technology you will develop may not earn you so much of accolades, but may actually earn you money. Industry only works on money. Okay. Okay. There are, so we now come to a point, since we are working on electronic devices, and the major material which makes most of the devices is semiconductor. Okay. As we all know, semiconductor word itself suggests semi, that is half. It's not conductor, not insulator, in between, and therefore it's a semiconductor. There are many semiconductors we are working at. We started with germanium in 47, 48. And for your information, in 2005, we are restarted working on germanium. Okay. So germanium was out 50 years, and we are now looking back to germanium. Most of the time we worked on silicon, which is still the major, material which every one of us work. The new other material semiconductor which we want to work or we still work is gallium arsenide, and the compound semiconductors, they are called 2,5-3,5 materials, gallium phosphides, cadmium sulfides, mercury cadmium telluride, 2,6 combinations, zinc sulfide. There are many such combinations. What is the word this combination I am talking? Let's say indium phosphide. Indium is from the third group, phosphorus is from the fifth group. So it is 8. Silicon is from the fourth group, which also has 2 bonds, 8. So it's trying to match that 8 number. Okay. So 2, 6, 2 plus 6, indium phosphide. Okay. So, sorry, it's the 3, 5, but you say mercury telluride, 2, 6. Okay. So you can always see a material which forms 8 groups and therefore can be a semiconductor. There are insulators, like which is the best insulator you know about? Which we use often. Glass. That's why I say we use often. Glass is an excellent electrical insulator. Okay. The version of glass which I use, glass is a single crystal material, glass, okay, which is also silicon dioxide, which is a single crystal silicon dioxide, is essentially the glass or the wood glass which you use. It's a diamond shape, bonding on that. Whereas if you have amorphous material out of it, which is silicon dioxide amorphous, that's what insulator we are using in all integrated circuits. So for us, the best insulator is, for integrated circuit is silicon dioxide. So all silicon devices became popular not because silicon was great, because when oxidized by simple oxidation process in a furnace, silicon converts into silicon dioxide. Silicon plus oxygen is SiO2, as straight as that. Okay. And that made the integrated circuit possible, because silicon dioxide is an insulator which does not allow any other impurity to go through it. It's impervious. So that became a great material. Then it also has a large dielectric constant around 12, 11.9. So if I put metal, say SiO2 and another metal, it's an excellent capacitor. It's an insulator in between. It has a large dielectric constant. So we started looking now that SiO2 is the real material which allowed integrated circuit progress. If that would not have been there, and that was the reason why germanium lost the race. Germanium oxide is not a good insulator. Firstly, to create germanium oxide is very difficult. It goes into 4 phases, Ge2O, GO2O, GO2O4. So since we don't know which one is a good insulator, and they keep changing itself by moisture, okay. So we could not use germanium oxide earlier, and therefore we gave it faster and went to silicon devices. Of course, there are the last part, of course, are metals. As I said other day, the most important metal we use in the circuit was aluminium. For 2 reasons: it has a good thermal conductor, it is a good electrical conductor, and third is it's damn cheap. Okay, it's damn cheap. So we used everywhere aluminium till say 2000, and I said later we figured out that the aluminium is not the best electrical conductor. It has finite resistance. So if you are now looking for a current to go from one point to the other of an aluminium wire, even if it has a thicker wire you put, there is a finite resistance. That means there is a finite voltage drop, which means the signal starting from here will get delayed to reach here, because there will be some voltage drop and there is some capacitor associated. So we started looking RC time constant. Oh my goodness, now this RC earlier when we were working on megahertz, this RC was in gigahertz, so we never bothered about 1 upon RC was much higher in gigahertz. But when we started working on gigahertz, then we worried, oh, they are the same times. Okay. So if signal takes as much second to reach somewhere, then what's the point, because it's already delayed by 1 cycle. Okay. So we started looking into different ways of looking in this area, which is essentially we are looking for different materials now. And one of the most important material which we have said last time is what? Copper. Copper is the best electrical and best thermal conductor, okay, together. And therefore, but what was the problem I said last time? So, we are now looking for copper, which is a dopant material in silicon. So it will give some traps in that. So it spoils the device. So we said don't use copper in silicon devices. But now we figured out we can stop copper going in through something called clad, and which does not allow copper to get in, but signal will flow on copper. So that's the newer process. As I said, IBM did this, Texas Instruments did this, and now almost every new circuit will have copper interconnects. There are different classifications of devices. Number of terminals is one. One of the way we can see, if a semiconductor device has 2 terminals, which device you are used in your lab? Diode, 2 terminals, okay, diodes. So most 2-terminal devices are diodes. Then there are 3-terminal devices, so we call them transistors. Like in the case of bipolar, we have emitter-base collector junctions. In the case of MOSFET, you have a source, drain and gate as the 3 terminals. Okay. So we say 3-terminal devices are normally transistors. And there are 4-terminal devices also available. These are called thyristors, PNPN or NPNP. These are 3 junctions, okay, and therefore 4 terminals. Okay. So there are 4-terminal devices. Where do you use thyristors? Anyone? No idea? Called semiconductor control rectifier, SCRs as the other name for that. No idea? For almost all power control in power electronics or any such power-based systems, you will require SCRs, or you require what we call thyristors. Okay, they are power devices. There is another classification which is based on energy transfers. Okay. So for example, if you are transferring electrons through an electric field, which are called electronic devices, that's what we exactly do. Electrons move under potential difference. Ohm's law, all that we are looking for, Ohm's law, related laws, not necessarily only Ohm's law. So these are rectifiers, BJTs, MOSFETs, all these devices are essentially based on electronic transport. Okay. Then there are other devices which are called photonics. They essentially transmit light or electromagnetic radiations. Okay. These are photonic devices like laser diode, LEDs, photodiodes, solar cells, and host of them. Okay. Now just to give an idea, what is the difference between electronic materials and photonic materials? After all, material cannot be different from other materials. It's a material, is that clear? It will have some atomic arrangements. So in some cases, when you are looking for atomic arrangements such that the electrons can occupy only certain states, upper state or lower state, and if it is in upper state, it is free to move. If not, it is bound and therefore no transport. Is that clear? That's exactly what we do in junctions. We see to it that electrons move freely. Okay, so transport. These are electronic devices. By same logic, if I say light can go or not go, which light cannot go? There can be, let's say, material which has a different dielectric constants, varying dielectric constant. It's also periodic. In all crystal semiconductor, they are periodic in nature. Same way, these also are periodic in nature. But periodicity in what? Dielectric constant. So what happens? Certain wavelengths are allowed to pass because electromagnetic radiation can pass. Certain will be blocked. These frequencies which are allowed to pass are called modes. Okay. And a bunch of together modes are called bands. Like in the case of frequency bands, 4 to 8 gigahertz. Similarly, we have bands and modes in the case of light or in the case of electromagnetic radiations. Now these materials is simple, like you will be not happy. I just put a silicon insulator silicon. This itself can act like a photonic material because interface of SiO2 and silicon has a periodicity in variation in dielectric constant. So a light can pass at the interface. So now I have a device in which electronics can be made and light also can be passed. These are called silicon photonic devices, which is the current craze in every communication surface. Is that clear? So we are looking for electronic devices where only electrons transport occurs. Holes is a similar transport like electrons. And in the case of optics or in the case of this, the materials, the electromagnetic radiation transmits. These are photons. Then there can be possibility that there will be under the influence of magnetic field, some action may take place, which is called MACFETs or MRAMs. Very popular memories are coming, which is called magnetic RAMs. This has much importance. Later someday we'll explain you. And finally, of course there are many, but at least finally, every system, you need to know temperatures. Okay. So thermometer we always have mercury, you heat. Instead of you may have a material which has some which you can say when heated gives you this kind of increase in their resistivity or something, which are called thermistors or which is resistance temperature device, RTDs. These can monitor the thermal energies. These are used in nuclear reactors and everywhere where RTDs are very important device. So it depends on the energy which is being monitored. Okay. Then there can be coupling between the two. What is coupling? Electro-optics. Just now I give an example. I can have energy of electrons and energy of photons interact. Okay. This is what we do in laser diode. In fact, we bias it and then shine the light, come out the light. So we have electro-optics on that. Is that clear? So all these devices depends on what kind of energy transport one is looking at is decided by another classification. Continuing with categories, diodes are rectifiers, diode 2 are negative resistance, There are certain devices, diodes or most resistors are what is the resistance property? That if you increase the temperature, the resistance normally increase. So you say positive temperature coefficient. Okay. If you have a diode, you have a similar property. But I want to have a device which has a negative resistance if I apply bias. Okay. So what is resistance does? It consumes power or dissipates power? I square R loss. Is that correct? So if you have negative resistance, what it will do? It will generate. So there are devices which generates power. But this is slightly misnomer, but we'll explain you. There are devices like gun diode, trapad diode, impact diode, avalanche diodes. These are essentially generators. Okay. And they have negative voltage current characteristic. If you plot, when I increase voltage, current doesn't increase but starts decreasing, which means there is a negative slope there, which essentially means negative resistance is obtained. So it will generate power. Okay. Essentially what generation means, it will do conversion of DC into AC. Okay. It's not real generation, but let's see what it is. Then there are devices which are called resistive devices, RTDs for example. Then there are capacitive devices used in sensors. Then you use two terminal switches on off. That's what we do most of the logic. Then we have transistors of three kinds using field effect, MOS transistor, potential effect, bipolar transistor. And finally third is called hot electron based transistor, HEMTs. Okay. Then there are memories, non-volatile, flash, यहाँ रख के घूमते रहते हैं ना, USB, flash. Okay. Thyristors, power device, light sources, LED, laser diodes, photodetectors, photodiodes, and solar cells. Bistable optical devices, just now I said dielectric on off, so certain frequency on, certain frequency off, switch. Then other photonic devices which I just mentioned, and of course there is a huge area which is called sensors. Okay, this is the history which I already discussed. You can see from here, this is diodes and these are transistors. Okay. There is a new device, modulated FETs or HEMT as it's called, came in 1980, which is made not of silicon but gallium arsenide. The other, of course, you can see here, right from resistive device to this resonant tunnel diodes, we are still working at. Okay. So these are essentially the devices which we are working. Before we quit, we just like to show you these are the processes which are used in semiconductor device fabrication. This course will not talk of fab. You, at least dual degree students of microelectronics, by their compulsion, whether they like or they don't like, they will learn VLSI technology course. If it happens to be that I still don't retire by then, next 2 years, I may be teaching one of those courses. So we need single crystal silicon. We need processes called oxidation. I just showed you silicon plus oxygen is SiO2, simple. We need diffusion, how to put impurities in and get inside is the process called diffusion. We need how to put by high energy impurities called implants. Then we can put materials by chemical vapor depositions, by chemistry, kind of at a high temperature because of pressure, it may react and generate something else. Use plasmas. Then you can do evaporations, then we can use chemical etching, plasma etching, and the most important process in all IC fabrication is lithography patterns as we transferring patterns, and finally packaging. Okay, so we'll stop here. Next time we'll show you something nano CMOS.